Okay, got an example for us. Let's apply method of sections to it. This is a truss structure. It is, as they're presenting it in what I'm pulling this from here, it's about 12 meters tall. It's in 3 segments tall, so 4 meters each. 3 segments, 4 meters each. And then this bottom segment attaches to the ground on a pin on the left here. And then if we come over to the right, it sets on a roller or rocker or roller on a horizontal surface. So it's not very imaginative, but that's okay. And then we've got triangles kind of going in and out all the way up the structure here. So we've got a triangle here. There's a horizontal member coming across here. And then that ties to a vertical member going right there. And then something like that then above here. So horizontal member here, going down to a vertical member there. And then there's a diagonal here, this one, where this one goes down into, well, anyway, you've got another diagonal member right here. I could try to describe it, or I could just draw 2 lines and you can see it. And then finally, we've got to finish this triangle off up here. Again, trusses are a series of triangles because they don't flatten very easily. So pin all of those connections. Forces applied. At the very top, we're applying 5 kilonewtons. And again, these are 4 meters tall. Each segment is 4 meters tall. So 4 meters below that 5 kilonewton horizontal force, there's now a 10 kilonewton force. 4 more meters below that is another 10 kilonewton force. And then 4 meters down to the pin, no force there except for the pin itself. And then it is 4 meters between the pin and the roller horizontally. And then finally, on this right-hand corner over here, there's a vertical down 5 kilonewton force being applied there. If we just go around in a clockwise fashion, starting here at the pin, calling that A, B, C, D, E, F, and G. The problem wants us to find the force in BF, BG, and AB. And of course, state whether they are in tension or compression. Okay. Again, when the problem's asking for specific forces and specific members, I like to either cross or check them or highlight them. We want AB. What else we want? We want BF. We want BG right there. Why do I do that? Well, it makes it, if I am going to cut this thing and apply method of sections, then it makes it easy to figure that out then, where I should lay that cut in. Right? Now, so we're going to need the force in these 3 members. That's what's asked for. Now, there's a neat trick we can apply here in a second, but the common approach here is always, if you can find your reactions, go ahead and find your reactions. Even if you can't, maybe you generate 3 more equations that you can use. So if we do free body diagram of the structure, it can be simple, doesn't have to be complicated. Make it where you can see it. 10 kilonewtons. I probably should have drawn this a little bit bigger. 10 kilonewtons, 5 kilonewtons at the very top, 5 kilonewtons down over here on the right. I've got G is a normal force because it's a horizontal surface here, a roller, so it's a vertical roller, or vertical normal force applied by that roller, I've got AY, and of course I've got AX over here. Yeah, I could probably have drawn AX in the negative X direction and been just fine. I didn't. And again, 4 meters are the distances there, all the way around, 4 meters. Okay. What do we want to do here? Pause, find your reactions. Let's keep this video kind of short. Go ahead and pause, find your reactions. All right, here's what I've got. I've got AX minus 25 kilonewtons. G, I took the sum of moments about A to get G. That's 50 kilonewtons. You could take the sum of moments about G to find AY, because AX passes through both those points. Or you could take the sum of forces in the Y direction. That had fewer terms for me. So I went ahead and wrote that out, and here we are. So I've got minus 45 kilonewtons for AY, positive 50 kilonewtons for G. Good to go. So we found reactions. Now, what are we trying to do? We're trying to find the force in these members. Do the reactions do anything for us? Well, honestly, I'll be honest with you. What you could have done is you could have taken a section right here, and you wouldn't even need the reactions. You could just analyze this top part of the truss, and the reactions don't even apply down here. We might still do that, honestly. But let's do this. I'm going to draw a free body diagram of this bottom part of the structure. So what I'm going to do is, you don't have to draw a straight line cut. You can draw any shape cut you like, but I'm going to do a cut through here. Now, you might look at this and say, Steve, there's 4 forces there. Yep, there are. There's 4. There's 4 unknowns. So you wouldn't be able to solve directly just with that information alone. You need something else there. Now, there's a neat trick we can employ. But there is this idea that I can now do a free body diagram of this bottom section, and I can write 3 equations for this, and I would have 4 unknowns. And then I could draw a free body diagram of this top section, and I could write 3 equations, and it would have the same 4 unknowns. So I could, between the 2 sections, I could write 6 equations for finding the 4 unknowns, assuming I've already got my reactions, which I do. Right? So without the reactions, I would have 3 unknowns down here plus these 4. I would have 7 unknowns. So I would need to at least find one of the reactions if all I did was the 2 sections and their free body diagrams. However, there is a neat trick. Note that BF is a 0 force member. How do I know that? Well, remember we said with 0 force members, there are 2 situations. One is if a joint has 3 members, joint F has 3 members attached to it, no external loads, no applied loads, joint F has no applied loads, joint F has 2 members that are collinear, and the third member is not in line with them, so therefore the third member, in this case BF, because these are collinear, BF is not in line with them. So all the force at this joint is directed along the axis of these 2, and there's no force left to be acted in this direction with these forces applied. If we applied a force here at F, that doesn't work. But because of the way this is set up right now, BF checks all 3 boxes for the first scenario of a 0 force member. Again, if you don't see that right off, you could look at this and say, well, I'll just make this cut anyway. I'll just do free body diagram of this part on top, free body diagram of this part on bottom, write 6 equations between the 2 of them, solve for the 4 unknowns, as long as you can find the reactions, which we can. Right? All that to say, if you don't see this, that's okay. If you don't see it right off, you don't have to. You can, if you wrote all 6 equations, you would find this mathematically. You would come to this conclusion. You would solve, and you would eventually find yourself solving to find BF is actually equal to 0. You would find it mathematically, and that's okay. But if you do see it, you're welcome to go ahead and employ that. So now I can go ahead and make this cut through here, and I can immediately set BF equal to 0 right off. So I'm going to go ahead and make this cut. Since I've gone to the trouble of finding the reactions, I'm going to cut through these 3 members. That only leaves these 2 members, A, G, and GF, are the only 2 members that I would have to draw a free body diagram of. So I'm going to draw a free body diagram of, we'll just call it the bottom section, whatever you want to call it. You could draw a free body diagram of the top section. Go for it. But I'm going to draw the bottom section. If you want to check with mine, go ahead and pause and draw it. See how you do. Okay. So I'm going to draw a free body diagram of this, what we're calling the bottom section. So that is in the bottom section, and I don't know why I'm drawing them as individual members. You wouldn't have to. I'm drawing A, G, and GF. Now remember, I found reaction forces earlier. I found G is a positive 50 kilonewtons. I had drawn that in the positive direction here, and I found it to be a positive 50 kilonewtons. Here I drew AY in the positive direction. I found it to be in the negative. So you can either draw it AY as positive and plug in minus 45 kilonewtons in the equations, or if you like, you can just draw it. We know it's 45 kilonewtons down, so you can draw it that way. That's okay. Same thing with AX. We drew it positive here. I found it to be negative. So I'm going to draw it minus 25 kilonewtons, or 25 kilonewtons in the negative x direction. Again, I've cut now through these members, so I've exposed their internal forces. I have an internal force AB. I'm going to draw it in tension. AB. I have an internal force in BG here. BG, that's BC, BG. I have an internal force BF. I'm going to go ahead and draw it, and we're just going to write that we're going to treat it as 0 force. I have force BF there. And then going up, I've cut through this EF as well. Four meters, and that's a free body diagram I can solve. If I come down here and I say, well, we know from previously BF is equal to 0. So knowing that, this is not unknown. Now I've only got these 3 unknowns, and I can solve. So if I do sum of forces in the, do I want to do forces or do I want to do moments here? No, you could, ooh, interesting here. I could take sum of moments about B. It's off the diagram, but I could take sum of moments about B, and this will not cause a moment about B. Only EF will cause a moment about B. I could take some moments about G, because these 2 pass through G, so they cause no moment. Only AB would show up in that equation. I might do those. I can, but notice since BF is 0, BG is the only unknown in the x direction. You know, if you don't want to look at this and say, if you just want to blindly say, well, sum of forces in the x, sum of forces in the y's, and pick a moment equation and solve it, you'll be able to solve it. There's no wrong way to do this. I'm just trying to look for easy ways to do it. But if you just want to go through and systematically sum forces x, sum forces y, sum a moment, do the math, you can do that. By the way, if you want to go ahead and do this, go ahead and pause and find you an answer, and let's compare. Okay, and in fact, I think I'm going to pause and write this out, because this video is starting to get a little long, so I'm going to pause and write this out. All right, here's what I got. Now, I didn't check the solutions on this. I could be wrong. I'm pretty comfortable with that, but if you got something different, check the comments, see if somebody else has gotten something different and corrected me, and I'll reply if they're correct. And you know, maybe you get something somebody else has said that's something else, and you agree with them. You want to agree with them, that's fine. Or let's just be positive in the comments. But all that to say, I think these are the right answers, and I haven't checked them. What do you think? What did I do? I took some moments about G. Why G? Because, well, EF passes through G, BG passes through G. I've only got A, B, and BF are unknowns. Oh yeah, BF's actually not unknown. BF's 0. So AB is the only unknown there. So this basically offsets this. That means AB is 45 kilonewtons in tension. And then once I know AB, solving the sum of forces in the Y is easy. That leaves EF is the only left over. And the only unknown in sum of forces in the X is BG. So we're good. Alright guys, that gets us through the first half of chapter 6. We'll start frames and machines next.